It's my first time in Romania. It's been quite interesting because Romania and Greece are very close together. Of course, I live in Greece. So it's one of the few places I can go to in the morning and go home in the evening. It's really so weird. It's like I woke up this morning very early, went for a run, a pouring rain, absolutely freezing, and came here, and this evening I'm going home again, so it's fantastic. But it's so close, I don't know why I haven't come before. Well, anyway. So here's a CPU graph on my little laptop, and you can see here that they actually are, it says they're 8 cores. It's a lie, they're not really 8 cores, they're actually 4 cores with hyper-threading. So I've got 4 physical cores and hyper-threading to help with the context switching, make that a bit faster, to get some of the data parallelism. And you can see at the beginning of the runs that there's quite a bit of black in the graph. See on the left side here, there's quite a bit of black. Now the black means that my CPUs are not fully utilized. That's what it means. The second graph is with using the managed blocker. And now you can see that at the beginning, there's far less black. You can see here, I've got a lot less black, and it actually also finishes about 8% faster. So that was my performance improvement with the large number I was trying to work out using the fork join framework together with managed blocker. Let's see how we get there. Now, Dimitri was talking about Fibonacci early on. I'm going to take it to a different level. We're going to work out a very large number of Fibonacci. And the problem with the standard calculations is that the numbers get large quickly, and if you take a normal, like, basic recursive function, it takes as long, the complexity is itself a Fibonacci series, so it takes a very, very long time. So, for example, if you want to work out Fibonacci 50 with the normal calculation, it'll take, I don't know, days probably. And Fibonacci 60 would take like thousands of days. And I tried to calculate how long it would take to work out Fibonacci of 1,000, and my estimate is 10 to the power of 200 years. That's a long time. It's a very long time. We're not talking about billions, we're talking about like a very big number. Okay, and the numbers get very large themselves as well. So you're looking at very large multiplications. Now, here's a naive implementation. I've got the function, the mathematical function is f of 0 is 0, f of 1 is 1, and then f of n is equal to the previous 2 numbers added together. And so you can see the sort of the picture is the spiral that goes around and around. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. And but this function has to calculate Fibonacci 1 over and over again, so many, many times. And as a result, it gets very, very slow. As I said, Fibonacci of 1,000 took me, well, it didn't take me, it would take 10 to the power of 200 years. So the obvious thing to do is to do this iteratively. So instead of using recursion, we're using iteration, where we only need to know the previous 2 numbers, and we don't have to work it out over and over again. With this algorithm, we can work out Fibonacci 1 million in 1.7 seconds. So that's, of course, fantastic. However, if you use a long, the number overflows around about Fibonacci 70 or so, and so your answer is incorrect. You get the answer quickly, but it's the wrong answer. Doesn't help us too much. So you could use Biglinteger, but there the add in itself is linear, so we're taking a linear algorithm multiplied by a linear add function, you get quadratic. Which is okay if you're working out small numbers, but if you're working out Fibonacci 1 billion or 100 million, it will take you too long. Unfortunately, there's a bunch of stuff off the screen. I don't know if this thing is sort of zoomed in or something, the projector. So I can do this. I can make it a bit smaller, and then we can fit everything on. There we go. So, whilst Andres fixes it. So what we can also do is we can take a different algorithm. No, it's actually a zooming of the actual lens. Don't worry about it. Oh, okay. Maybe that will work. Yeah, that works. Thanks. It's still zoomed in a bit, but it's better than it was. I thought, actually, it's no different. Sorry, no different at all. So here's the extra sum of squares. This is a better algorithm for working out Fibonacci. And instead of having exponential complexity, or in fact linear complexity, we've got logarithmic complexity. So that's, of course, much better. At every step, we're dividing the problem by half, and we can work it out much quicker this way. Now, the actual algorithm is logarithmic, but the multiply in Java still takes a long time, especially as the numbers get larger and larger. Now, the typical multiply that we learn in school, many years ago, is actually quadratic. It's order n squared. That's why the teachers used to torture us with these, here, do this calculation, because they told us, you won't always have a calculator with you any bigger, right? That's what they told us. So, at least in South Africa, where I come from, that's what they told us. And so the complexity is very bad. And in Java 8, they fixed that. They've now got two different algorithms inside Biglinteger. One is called Karatsuba, other one's called Cook. And Cook is for very large numbers, and for slightly smaller numbers, they use Karatsuba, and even smaller, they use the normal order n squared multiplication. However, it's still single-threaded. Now, we will fix that in this demo. So the first demo, we're going to try and implement the algorithm using Biglinteger. So I'm going to take this, and this is the algorithm. If it's an odd number, there's one calculation. If it's an even number, it's a different calculation. And we'll try and code this using Biglinteger. Now, what I'm going to do is I'm going to do the coding step by step, and every step that I code is going to be checked into SourceSafe, into GitHub, so you can look at it afterwards and see how I did it. So this is first of all Fibonacci, and hopefully everybody can see that. And we're going to say int half equals n plus 1 divided by 2. And this is going to be used for both of the calculations. Then we're going to say Biglinteger of f0 equals f of half minus 1, and f of 1 will just be f of half. And then if n is odd, so we say if n percentage 2 is 1, now we could use bit masking, but the compiler will actually do that optimization for us. So we don't have to worry about that optimization. If n percentage 2 equals 1, we're going to say return f0 dot multiply f0, so we're going to square f0, and we're going to add f1 dot multiply f1 to that. That's if it's odd. And if you look back at the slides, you can see that it's the same calculation over here. Now, if it's even, then we're going to say return. We need to multiply f of 0 by 2. And of course, the programming trick is to shift left by 1. We all know that. We're going to add f1 to that, and then we're going to multiply the result with f1. And if you look at the formula again, you'll see that that's exactly what we're doing over here. F of 0 is f of n minus 1 over here. F of 1 is f of n. Okay, now, what we need to make sure that this actually works and runs correctly before we get too excited about this. And let's run it. And I've got a whole bunch of tests here, and we'll see if it actually runs through. Now, it's going to take a little bit of time to run this. And whilst it's running, I need to just quickly show you the CPU history. This is the CPU history whilst it's running. We can see that there's actually only one core really busy. We don't have all 4 cores busy at the same time. Because it's a single-threaded experiment here. There's no multi-threading at the moment. We'll get to that, but first we want to get it working in a single-threaded environment. And it takes normally takes about 40 seconds or so. I'm sorry, I wish I could be faster so I don't take any of your time in the next session. But we'll speed it up in a moment, and hopefully we'll have enough time for Andres' talk afterwards. So we can see here that it took 44 seconds to run through this, right? So that's the first experiment, 44 seconds. And what we'll do is I didn't want to do that. Keep that open. let's go and hide that away down here. And I'm going to just change something here for a second, because I want to do it, I want to stay in this view. I think this is okay. Now, before I do anything else, git commit demo 1. So if you get my GitHub afterwards, you can see all the different steps I took to solve this. This is the first experiment. The second experiment is we want to parallelize this a little bit. And what we're going to do is we're going to do this by simply creating a recursive task, which is actually a fork join task. We're going to run that in the background, potentially, with work stealing, right? Hopefully work stealing. And if you just say fork like that, it actually by default uses the common fork join pool. You can also specify a different fork join pool if you want to, but by default it uses the common one. So that's what we'll use. And the common fork join pool is normally sized according to your physical hardware by some relation. So it probably is going to utilize your available hardware. All right, let's go and do this and see if it makes a difference. So we're running at 44 seconds. We want to make this faster. And we're going to take the first big integer calculation, and we're going to say Fibonacci, a fork join task of big integer, f naught task equals new recursive task. And here we're going to return this over here. We're then going to say f naught task dot fork, and then we're going to do the second calculation, the f of half, and in the end we're going to say f naught task dot join. Okay, so this then does it in parallel, and hopefully this is going to make it faster. Now, I need to see how many of you are listening. You're listening. That's great. Pardon? How much faster do you think this is going to be? 40 times. Maybe. I've only got 4 cores, so that'll be quite an achievement to make it 40 times faster. Any other ideas? About? 4 times faster, or a fourth faster. So 25% faster. Okay. 3 times faster. Okay. Good. Let's try it out. There's only one way to really know is to run it. And you can now see that we are utilizing all the available hardware. That's fantastic. Okay. Oops. Not anymore. So we started off great. We started off utilizing all the hardware, but pretty quickly we dropped down to just using 1 core again. We first went from using 8 cores to 4 cores to 2 cores to 1 core. And it's a very common characteristic of this type of fork join algorithm that when you have to eventually merge the results together, that's when you have to start doing single threaded. It's like if you do a merge sort, at some point you have to merge the final result, and that could be your most expensive operation. All right, now, if you do a profile of this, you'll notice that where we actually are spending our time most in is multiply and square. Right? Multiply and square. And those 2 functions are inside big integer, and they are not parallelized. So we eventually become single-threaded. It's a lot what you were saying this morning. So I'm going to do another commit, demo 2. And we're going to now try and also parallelize big integer. Now I'm going to do some trickery here, some nasty trickery that actually works really nicely. And oh, that's a good question. Thank you for asking that. You guys really are listening. I love it. That one took 21 seconds. So it's roughly twice as fast. Okay. Pardon? Right, so about 20, and we've done a lot of work. You know, we're using the hardware in the beginning very well, but once we get over the first bit, once we have to start multiplying larger numbers, then that starts becoming too slow. Right, fantastic. Now, so 21 seconds, 44 seconds, round about there. So it's about half of the previous number. Now, what I want to do is I want to apply the same idea to big integer. So what I'm going to do is I've got a different package here called math hack, right? And there's a package there called java.math. And what I'm going to do is I'm going to go to big integer, select it, copy, go to here and say paste. Yeah, I love cheating. Okay. So now I'm going to change the Java math big integer. Okay, and if you look at the multiply method, no, I'm not extending the class. I'm copying and pasting the Java JDK class, and I'm going to change that class. There's no extension here. I'm hacking it. It's called the math hack module, right? Math hack. And I've even, thanks to Andres, I've even put in a different license file for that one. Because that's what's it? GPL, right? With the class file extension. So we've got the multiply. And inside the multiply, there are two different multiply Karatsuba and multiply Tomb Cook. Now, the multiply Karatsuba is for numbers which are big, but not that big. So we're not going to get that much win out of parallelizing that. We're going to just do multiply Tomb Cook. And the way it works is that they take the number, the large number, and they split it into 5 equal chunks. Then they do some magic. I don't know how that works. I'm not a mathematician. And then in the end, what comes out is the correct answer, hopefully. Okay. And so what I'm going to do is I'm going to basically, oh, no, come on, I've gone to the wrong file. Okay, I must go to this one. Okay. So it's multiply Tomb Cook. Okay. So I'm going to fork the first multiply. Then I'm going to do a bunch of other stuff, do a second multiply with the current thread. I'm going to then join the one that I forked. Then I'm going to fork again the next multiply, do a bunch of stuff, and at the end I'm going to say again, here I'm going to say join, to join the second one. So let's do that in code. So we're going to say, first of all, we're going to make a multiply task. It's going to be v0 task equals new multiply task, and we're going to pass an a0, comma b0. And of course, this class doesn't exist yet, so let's create it. Create inner class multiply task, and we're going to also have a constructor that takes an a and a b. Actually, just want a and a b, not a and. There we go. Come on up. And we'll have also parameters for that. And this multiply task is going to say extends the recursive task of big integer, like so. And then I compute, in the computer I say return a.multiply b. So that's actually, that part's very easy. In fact, all of this code is very easy. This is not rocket science. And we're going to do the same thing for the square task. I'll need that in a moment. But here we only have one. And we're going to just say over here, a.square. There's actually a method called square, but that one is not accessible outside of big integer. It's private. So, but it figures out if you're trying to square a number. If you have two equal multiplications, it calls square for you, so you don't have to do it yourself. All right, let's get back here. After I've created my multiply task, I'm going to say v0 task.fork. And then once I've done all the other calculations, I'm going to join the v0 task over here. Okay. Okay, and we'll do the same thing for V1. Multiply task, V1 task equals new multiply task. This time it's DA1, comma DB1, V1 task dot fork. And at the end, we're going to join again. We're going to say V1 task dot join. Now, the multiply is only one part of the calculation. The other part is the square, which is also very important because the square is roughly half the time we're going to be squaring. So we need to look for square tum cook and do the same thing there. We're going to, it's 5 equal chunks. We're going to have a square task. V naught task equals new square task of A naught. V naught task dot fork, and I'll double check that I've forked everything in a moment. And then after I've done the add, I'm going to say V naught equals V naught task dot join. And the same thing for V1, square task V1 task equals new square task DA1, V1 task dot fork, and at the end I'm going to say V1 equals V1 task dot join. So I've hacked into existing code, and now my Biglinteger is parallelized. Now I want to just double check that I'm forking it. Let's go look where the multiply task is being used. Fork and fork. Yes, I'm forking everything. So in theory, this should run. It should run if we did everything correctly, which is extremely unlikely, given that I woke up at 4:30 this morning. So we'll see. I'm just commenting out some tests which are not necessary to worry about. All right, let's run this again. Now, it's going to be exactly the same speed as before, because when you run code, if you can create a class called Java Math Biglinteger, but it's not going to be used, right? Because when you run it, it's going to use the one from the JDK. So we've had, actually, it did run accidentally. I forgot to change something, which is, there's this thing called xboot class path, which I thought was at /a, but I was playing with this early on and I forgot to put it back. So what you can do is you can prepend the class that we created, the Biglinteger class, to the normal boot class path. So if I say /a, then basically our Biglinteger will not be used. So let me run that again. So this is how it was before. And you'll notice now that in the beginning, the CPUs are all at 100%, and then they go down very quickly. So this is the standard Java Math Biglinteger. And now I'm going to stop that. It's going to take about 23 seconds. And if I change my VM options to be -x boot class path /p, which means prepend, so prepend the boot class path with my output for my own little Java Math Biglinteger, my hacked version, then it uses that one, and you'll notice now that the CPU is running hot, and it stays hot for most of the way. Don't say it's cheating, it's optimizing, right? So I've made it faster by quite a substantial amount. You can see that before it was running about 22 seconds, now it's about 15 seconds. I had it running early on at 13 seconds. It's sort of, there's a lot of GC going on, a lot of background optimization, which we're not always sure what's going to happen exactly. But now, let's look at this some more, because we can, before we do anything, let's first commit demo 3. Now what I want to do is I want to measure how long each of the multiplications actually takes. So what I'm going to do is I'm going to wrap this code in a little where I'm measuring the time before and afterwards. Now I can't do this every single time because current time millis is a very expensive method to call. So what I'm going to do is I'm going to say I only care if n is bigger than 1,000. Then I'm going to look at the time millis. Otherwise, I just use 0. And the same thing here, I'm going to say if n is bigger than 1,000, I'm going to work out the time, otherwise 0. And if time is bigger than, let's say, 50 milliseconds, then print out the time. Now, when you run it, you'll see where we're actually spending our time. Okay? No, we actually don't. You just see how much time we're spending. So you can see some of these calculations take quite a long time, but I also want to print out what the calculations actually are. So let's do this. Let's say fib plus n time. So we can see where the time is actually being used. And okay, so look at the numbers here. And see if you notice anything about how long they take. Anybody spot anything here? Exactly. So there are lots of duplicates. You can see here you've got this one being, especially before, this one was worked out here, and it was worked out again over here. Okay, so so there are lots of duplicates being worked out, right? And so the obvious thing to solve this is to put in a cache, right? A temporary cache. We don't want to have a memory leak, so we'll have just a temporary cache. And what we're going to do is we're going to make a map of integer, comma, big integer, cache equals new. Now it's got to be thread safe because multiple threads will be using it. So we're going to have here a concurrent hash map. And whatever you do, don't use compute if absent. Ever. Don't use it. Why? Do you want to know why? There are two reasons. The first reason is that it can cause absolutely horrible contention in your system. Because even though it's supposed to be like, concurrent, it does blocking. You love blocking, Dimitri. So it does, you hate blocking, yeah? So, and it's especially the case if you've got entries which, if you don't have that many unique keys in your hash map, and you have a pretty high probability of multiple threads trying to access them at the same time. Secondly, if you accidentally modify the structure of your concurrent hash map whilst inside your compute function, you can get an infinite loop inside your hash map. That's not so good. So there are two reasons why you should never use compute if absent. Okay, so we're going to put in here 0, 0 and 1, 1. And then we're going to say return f of n, cache, where this is going to have also the cache here. So we're going to just use the int n, the cache. Now, something that I often do is I rename a function or add a new parameter and I forget to call all the correct functions. So what I'm going to do is I'm going to just mess this up by giving it like a really wrong name. And that shows me all the places where I didn't use the cache. There we go. So there's, if I could type, that would help. So cache over here and half, cache over here. And then I can change this back to just being f. And let's make this second function to be private. Now inside the f, we're going to do the following. We're going to say big integer results equals cache.get of n. If results is null, then we do the whole calculation. And down here where I say return, I'm going to say results equals, and results equals, and after the finally, I'm going to say map.put, not map, cache.put n, the results. And have I done this right? Return the results. And that should be correct. So now, we were running about between 13 and 15 seconds before. Now, we're going to try it again. The problem with this particular algorithm is that there is a pretty high probability that we still will work out the numbers at the same time. So we have improved things a bit, right? The total time has gone down to 9.5 seconds. But we could do better by avoiding having multiple threads work on the same number. It's like we run this one conference on Crete that Andres helps me with called JCrete. And the 1 year I went and updated our wiki, and I spent hours updating the wiki. And once I finished, one of the other organizers, Rabea, told me, oh, I've also done that. So we both did the same work, and we both spent hours on this stuff, because neither of us said, hey, I'm going to do the wiki now. So we completely wasted our time on this stuff, and we don't want to do that. We don't want to duplicate time. So it's better to put up your hand and say, I'm going to do that. Now, you could do this with computable futures, but I didn't quite manage to do what I wanted to do, so maybe you can help me with this afterwards. But let's just try to do it with another mechanism where before I start working, I want to find out, is somebody else working on this already? That's all I want to do. So what I'm going to do is I'm going to define a special big integer that means I'm working on it. I'm working on it. So I'm going to say here, private final big integer reserved. Oh, before I do that, git commit demo 4. Was it demo 4? I can't remember. Yes, demo 4. That was this one. Good. Okay. So reserved equals big integer dot value of minus 1,000, some number, some large negative number, and then what I'm going to do, instead of saying get, I'm going to say put if absent in comma reserved. Now the first thread that calls that is going to put in the reserve value, and it's going to get back the value null. So if you get back null, it means you were the first to put in reserved. So you can start working on it. If you get back reserved, it means somebody else is working on it. So you're going to wait for them to finish. And if you get back anything else, then that's the result, you can return it. So that means that if we, if the result is reserved, then we want to wait for somebody else to finish it. So I'm going to just take a pause and let somebody else do the work. Now, Dimitri's going to hate this, but I'm going to do it anyway. Synchronize reserved, while results equals cache.get n is equal to reserved. And here I'm going to say reserved.wait. Now, we might have multiple threads waiting on the same object, but hopefully it's not going to happen too often, and that's the actual contention on the wait notify is not the bottleneck here, so we're not going to worry about that part. We do have to worry about the try catch. I'm going to say throw new cancellation exception, interrupted, like so. And then what I'm also going to do is, once I've put it in, I'm going to send a notification to anybody who might be waiting on this information. Now, let's run it, and we'll see that hopefully we're only going to work out each number one time. And you can see it here. You can see here that the calculations are only happening once. And look at the speed. Down to 7.2 seconds. Now that's actually quite amazing. You'll be even more amazed to realize why I'm so amazed at that number. Because if you take the big integer and put it into a different package to Java Math, it's slower. Yeah. By like 20% or something like that. So that's why, look at this. I discovered this like, Andres is shaking his head. I have no idea, to be honest. I discovered it as I was preparing for this talk, because in previous talks I would always put it into its own package. And when I ran it, I thought, wait a second, how can this be faster? It doesn't make any sense, right? my intuitive imagination is not necessarily JIT itself, but I think that they might have some intrinsics for big integers for smaller numbers to multiply them faster. I don't know, to be honest. That we all cheat. Everybody cheats. You know, I could always say it's because of mechanical sympathy. And I'd probably be right. It is probably something to do with that. I could say it's because the big integer class is one of the first that's loaded, or some other nonsense. But I actually don't know. This was, as I said, I just discovered this as I was preparing for this talk, like half an hour ago, and so I don't know. I haven't had time to research it yet. But it's interesting because it seems to be quite consistently the same like this. All right, now what I want to do is I want to run this again. I want to show you something. Before I do that, I want to just push this. Commit demo. This was demo number 5. Okay. I want to run this again. I want to show you something which is not so easy to see on this particular graph. Sorry. But if you look very carefully, you'll notice it. Okay. If you look at cores 0, 1, 0, 2, 4, and 6, those are the real cores. At the beginning, there's a slight blip where it's a bit too black, right? It should start off with everybody running 100% CPU. And the reason is that at the beginning, there are actually quite a few threads which are idle, waiting for others to finish. And you can measure this quite easily. You can go and where at the moment I'm just waiting. I could see how long did I actually wait. So I could do the same thing that I did before. I could say long time equals system.current time millis, and I don't know if this is going to be if time is bigger than 50, waited for. So I'm not sure what this will output. I think I have tried it, but I don't remember what the output was. You can see that there is idle time. So threads are not actually working. They especially at the beginning, right? Once the system starts going, then it tends to work well. But in the beginning, there were a few times where I was waited for 1.5 seconds. Now, it happens to work not too badly in my machine because they cheat. You seem to like this word of cheating, right? We should have a program for Java programmers called cheaters. Where do people cheat, right? So the problem is that, well, not the problem, the way they do it is that they actually, they have the number of hardware threads, number of threads inside the fork join pool, the common fork join pool, but only have 4 cores. So they've got twice as many hardware threads running as can actually work at the same time. To really do calculations, number crunching at the same time. So even if I've got some threads which are idle, I can still get a fairly good utilization because I've got too many threads actually running. Now, I can show this to you by doing some thread dumps.
Actually, here you utilize all the double sets of the registers actually so it's really faster than just.
Yeah. Okay. So there is some parallelization going on, right? For the context switching would be faster than if you didn't have hyper-threading. But you're not going to get 8 times speed up, not with this type of system. Now, what I wanted to show you here is if you look at the output of the thread dump, let's go and you can see that here the thread is waiting. So there are quite a few threads which are waiting on object monitors. There's some which are doing some work. At the beginning, especially at the beginning. That's why at the beginning there's this part where it's black and then it starts going green. Once we've broken the numbers down into enough different fork joints. So in the last demo we're going to address this last bit, and that is the fork join pool has the ability to create additional threads if you're blocking a thread. So if you ever block a thread, you can say, if I'm blocked, then please perhaps construct another thread to keep the parallelism the same. You see, the whole thing with fork join pool is you can't specify the maximum number of threads in it. You can only specify the desired parallelism. How many threads do you want to run at the same time? There's no maximum, right? So what we can say is, if I need to wait, then you are allowed to construct additional threads in order to keep the parallelism high. All right, now before I show this, I wanted to ask you a question. How many of you are subscribed to my Java Specialist newsletter? Nah, not subscribed, shame on you. So if you're interested, javaspecialists.eu, there are like over 250 to catch up on, so good luck on that one. Have fun. Now, what I wanted to show is how can we manage this better? So what we can do is we can create something. We're going to call it the private class. Let's call it a reserved blocker. Implements a managed blocker. Now this is an interface from the fork join pool, and it works specifically to alleviate this problem where some threads might be blocked for a while. The only synchronizer which implements this already is the phaser, the Java 7 phaser. Nothing else does this. So here, we need to implement two methods, block and isReleasable. And basically, isReleasable is my precondition. My precondition? No, my conditional, my condition predicate of my wait, which is basically this over here. This is my isReleasable, that part. So if I take this and I put it in here, return is not equal to reserved. So if it's not equal to reserved, I want to exit. Now, I need to create fields for this. I'm going to say private, I'm going to make it a volatile field because I'm going to exchange information between it. Results. I'm going to have the cache also stored inside here. So let me just take that definition down here and say private final map and private final int n. So these are my two fields I'm going to pass in are n and the cache, and what I give back is the results. And I still have another 2 minutes, I think, to finish this. So the block will do the following. Block will be like the block up here, synchronized reserved. And it's going to be synchronized reserved while not isReleasable, reserved dot wait. And then in the end I'm going to say return true because I actually was successful. Okay? So I've taken the wait code before and I've put it into an interface. And then the only thing I need to change is in here, we have got this while. I'm going to take that out. I'm going to say here, reserved blocker. Blocker equals new reserved blocker. Passing in the n and the cache. Then I'm going to say, no, I'm not going to say blocker.block. I'm going to say fork join pool.manage block of the blocker. And then I'm going to say results equals blocker.results. And this managed block takes care of maybe constructing additional threads for us if we need this. Let's run it again. Now, in this particular experiment, you won't see, you won't actually see a big performance improvement. There's a small one here. I mean, this might just be a fluke, the fact that it's a bit faster. It's just the demo gods are trying to make me feel happy for being in Bucharest, right? This is Bucharest, isn't it? Okay, just making sure. Well, it's certain Natal, so it could be anywhere, right? Could be in America, I don't know. So it's actually it's a bit faster, but if you run this a few times, you get a variance of results because a whole bunch of other things going on in here as well. Now, interestingly, is if you look at the CPU history we can drag this up, it's a little bit less black at the beginning. All right, but because it's a small number, you don't see the difference isn't as pronounced. It's more pronounced if you look at this this demo I showed at the beginning, the slides, where I worked out, I think it was 250 million or 1 billion, where at the beginning it was a longer time before we started getting 100% utilization. Now, at the moment, the only class which is implementing this managed blocker is Phaser. There was talk about doing this also for reentrant lock, and in my newsletter, one of them, I can't remember which one, I've implemented that just for fun for reentrant lock, and then I've also applied it for linked blocking queue and for arrow blocking queue. So for both of those, you can do it. And this is basically how you can make it go faster. Any questions?
Exactly a question, but don't forget to push the 6.
Thanks. So there's, okay, you can find this on GitHub /Heinz what's actually my GitHub? I'm not sure actually, to be honest. All right, this is my website, but that's not the way it is. It's on GitHub, Kabutz, Kabutz. And if you look at my repositories, just search for Bucharest, Turbocharge Managed Blocker Vox Bucharest 2017. And yeah, well, you'll find it. This will be demo 6. And I actually made a mistake because I didn't add the math hack source in there. So let me just do that again. This is now the final one with hacked cheating Biglinteger. Pardon, sorry?
Today we have invented cheating.
So that's it. Thank you very much for listening. Thanks for your great participation and comments and helping me when I got stuck. And enjoy the rest of the conference.